Okay, so now our AP Lit wasn't bad. Thank you for talking back to me so I don't feel like I'm completely alone by myself. AP Lit wasn't bad. That's good. That's excellent. So I'm hoping that that's kind of going to be everybody's experiences, that they feel like the stuff they did prepared them for the AP exams that they're taking. So that if you were hoping to get college credit for stuff, that like it actually happens. And got the guys out mowing their lawn this morning. I don't know what is the landscape guys in my neighborhood start at 9 because they're out there mowing like they always seem to be in the morning. Okay, so what are we gonna do? We're gonna talk about area between two curves, which is just going to be an application of integration. So not really a lot of new today. The new part will be setting up the integral to solve, but the antiderivatives that you have to find and using the fundamental theorem, none of that is new. And actually, I don't even think I have any e's or natural logs or anything kind of scary in there. It's just some basic polynomials. So my thought is this week we're going to talk about how to do this. And then next week we're going to talk about why you would want to do this. And then have some ideas for our last class. I haven't fleshed them all out yet, but I'm sort of thinking, but we'll kind of keep those working on that, trying to do something like not totally lame for our last meeting. So, okay, but today we're going to stay lame and we're going to go calculus. That's my job officially. So let's go ahead and take a look. This document, it is put on Blackboard. I meant to email it to you and I didn't. I apologize, but you're probably fine with that because you're like, I'm over email. But it is already up on Blackboard. I think. I can't remember if I copied it for second period or not. Okay, I'll double check. But if it's not, it'll be there. But so remember that when we're finished, I will get a video of our session. I'll upload a link for that for YouTube. I'm like a YouTube star now. And I will upload the notes. So you'll be able to follow the notes to do the handful of practice problems I have. Alrighties? Alright. So enough blah, blah, blah. Let's talk calculus. Alright, so we're going to go area between two curves. And chat is open if you want to throw something in chat or if you need to raise your hand and I can give you a mic. So, two functions. And one function is definitely bigger, higher than the other. So there's essentially a top function and a bottom function. Now, just for our sake of notation, in our examples, our top is F and our bottom is G. That is not always the case. So don't assume that just because we use letters F and G, just because we use letters F and G, that F is automatically top and G is automatically bottom. Okay. So if we want the area between F and G, we set up an integral of F minus G, top minus bottom. And the limits of integration, the A and B values, are from sort of a left and a right boundary. Okay? Now, the left and right boundary of the region that we're calculating the area of. The left and right boundary could be created because the two curves cross and we're going from intersection to intersection. That's one scenario. Another possibility is we just sort of pick a left and a right boundary, and these, when we're doing the area of in this direction with tops and bottoms and left and right boundaries, our left and right boundaries are x equals, and our top and bottom functions are y equals. So y equals a function, y equals a function, left boundary, right boundary. And in this problem, I'm sorry for the double coloring, but this is the blue area, all right, is what we would be calculating. And so weird shapes, you know, things that you typically wouldn't have a formula for calculating the, you know, area of a eyeball looking shape or whatever that is. We have a calculus technique for doing that, okay? That is grounded in geometry because it's an extension of a really, really long, complicated Riemann sum with a lot of rectangles. Okay? So our job today will be to calculate these areas. In some cases, I will show you a picture of the area. In other cases, we will start with the functions and identify the area and then calculate it, okay? So that's the plan. So, and then, like I said, next week, why do we care about this? What can that area represent? What real thing would you do in the world that would be an area between two curves? And I will give you a hint. It's going to be an economics thing, and it's going to be a supply-demand function curve graph. Okay, sorry for the extreme blurriness of this. It's pretty bad because I snagged it and it's already not focused. But when you actually have your document, it won't be so furry. So in this case, I have the two functions curves graphed. I've got the x squared plus x plus 2. Actually, I'm going to be a geek. X squared plus x plus 2 is this guy. Okay. It's a piece of a parabola, got a little bit of a curve. When x is 0, y is 2, crosses the y-axis at 2. So that's a couple ways we can identify that this is the x squared plus x plus 2 curve, and that this guy is the y equals negative x curve. And this problem is going to ask us to calculate the area between these two curves from x equals 0 to x equals 1. And so I'm going to play with my technology a little bit. Look, it's a crayon. Oh, it's coloring. And it feels just like it's so soothing to color. Little adult coloring books and stuff. Okay, so that shape. Kind of trapezoidish, but with a curved side. That's the area we're going to calculate. All right, so integral. Top function, x squared plus x plus 2, minus bottom function, negative x. Okay. I'm going to throw a dx on there because that's part of the way you write an integral is you indicate that's the variable of integration. And my limits, 0 to 1. Left boundary, right boundary, top, bottom. That's the new part. Putting all the pieces together to create the problem that will calculate the integral. Okay, if you're looking at that and you're unsure why I put this first and that second, or where these came from, or if you have another question kind of in that realm, feel free. Okay, I'm playing around with my markers. Now, what happens next? Well, I think for me, didn't agree. It makes sense to kind of simplify inside before we do the antiderivative. So how about let's make this from 0 to 1, and then this will be x squared, and then plus x minus a minus x makes plus 2x. Sorry about that. I know that's driving you crazy because I'm drawing it different colors. You can tell I'm not super OCD about stuff like that as I write things in a million colors every time. So x squared, yep, plus x minus x is another plus x, so it's plus 2x total, plus 2. All right, so simplify, combining like terms, good plan, if possible. Next step, I do my antiderivative. So antiderivative is going to be x cubed over 3 plus, hoping we're okay with antiderivative of 2x is x squared, plus 2x plus c evaluated from 0 to 1. Okay. My fun, just little notation kind of convention is to kind of keep track of these so you don't lose them. So I'm going to take the antiderivative, but my answer is not the antiderivative. My answer is going to be the value of the antiderivative when I apply the fundamental theorem. So that means I'm going to plug, oops. So this is going to be my FTC. I'm going to plug in 1, and I'm going to plug in 0 to my antiderivative. So 1/3 plus 1 plus 2 plus c minus 0 plus 0 plus 0 plus c. Now, yeah, I mean, if we were doing this like on an AP exam, they like to see that you understand that you know you had to plug a 0 in here. So 1, 0, or like just 0 plus c would be sufficient. I'm just doing this so you can understand like what happened. 1 in here, in here, in here, bam, bam, bam. 0 in here, in here, in here, bam, bam, bam. You don't really need the c's because they are always going to subtract away. And so final answer to this is 3 1/3. Okay. 3 1/3 what? Depends on what the context of the problem is. Okay, there's lots of different things we can do. There's a lot of different applications that involve area sandwiched between two curves. So that's it. That's the most basic, I think, type of problem where everything is given to you. Your function equations are given. The graph is given. I guess the only thing that's not explicitly given is which function is which, but you could figure that out even just by graphing it yourself on your calculator. But with a little bit of experience, hopefully we're cool with the negative x line being that, and so by default that having to be the parabola. If you flip-flop these, you'll know it. Your answer will come out negative, and that doesn't make any sense in these kinds of problems. So that's an indicator that, like, oh, I mixed up top and bottom. Okay. Or you can also do that if you mix up left and right. So just got to be careful. If you actually mix both of them up, you'll get the right answer, which you 2 wrongs making a right. All right. So that's problem type 1. Everything pretty much spelled out for you. Problem type 2. Sorry, I'm being like weird. Okay, problem type 2. So once again, we have the graphs given. The 2 function equations are different enough that hopefully we're okay with understanding that this is the top, the parabola 6 minus x squared is the top, and the y equals x is the bottom. What makes this problem slightly different from the first one is we don't have the left and right boundaries explicitly stated in the problem. We are supposed to get those from the graph behavior. We're supposed to look at this and go, okay, there's my left boundary and there's my right boundary. I need to identify those. Now, graphically, in this case, piece of cake. You've got a very clear shot that x equals 2 looks like this boundary, and hopefully you're able to see that x equals -3 is this boundary. Other options, create the graph on your calculator, and your calculator can tell you by asking it to calculate the intersection points. You can also look at the tables for these two functions to identify intersection points, the left and the right. Or if you prefer to kind of do some algebra, 6 minus x squared equals x. The solutions to that will give you the intersection points. Now, solving that, it's quadratic. I like my x squared term to be positive, so I'm going to move everything over to the right. So how about 0 equals positive x squared, positive x, minus 6. And so that way it's in standard form, x squared is positive. This one happens to factor quite nicely. Plus 3 and a minus 2. And so x equals negative 3 and x equals 2. Just like we can see on the graph. Okay. So if the implication is I want the area between two curves, but it doesn't seem like they're giving you a left and a right boundary. Okay, we can do the left and the right boundary. Assume that we're going to do that through intersections. Okay. Where do they intersect? Where are their natural boundaries created? All right. Now, setting it up. Remember, we're going to integrate top minus bottom, left boundary, right boundary. So negative 3 to 2, 6 minus x squared minus x dx. Now, in both these cases, the quadratic happened to be on the top. That is not always the case, so don't make that assumption. If you're not sure which one's top or bottom, looking at a graph is going to be important to help verify that. Okay, I'll stop for a second there and see if let you guys kind of catch up there, see if you have a question about what's going to happen next or how I got to this part. Hopefully you're okay with now taking this setup and kind of finishing the calculus. Right? And that's what we practiced last week. We practiced or talked about our antiderivatives. So 6x, sorry, that's a minus x cubed over 3 minus x squared over 2, evaluated from negative 3 to 2. Yeah, and I'm getting lazy. I'm not writing the plus c because I know it's going to subtract away. If we're doing fundamental theorem in my antiderivative, we typically don't write the plus c. And so this guy, this is where your calculator work, you've got a 12, you've got minus an 8/3 minus 2 minus negative 18 minus negative 9 minus 9/2. It's always tricky when you put a negative in and then have a negative behind it. So the negative 3 cubed is negative 27 divided by 3 is negative 9. So it's minus a negative 9. The negative 3 squared is a positive 9. So this is positive 9/2. And then you subtract it. Okay. Now, I'm not going to demonstrate my awesome arithmetic for you. I know you guys love it when I start like adding and subtracting things in front of you. But I'm just gonna grab my friend the calculator here. And so this is gonna be 20.83 repeating, which fraction wise is 125/6. Okay. I know that many of you know how to get this without doing this. Okay. I've seen it, and some of you are like, I don't know how to do that. That might be something we talk about. Okay. I'm looking for this and this part still now, okay, as part of, evidence of our calculus skills. So there are calculator tools for evaluating this. You can, if you have the right calculator with the right operating system, type that in and get this approximation for it. Okay. All right. So how are we building things up? Well, number one was kind of everything given. Equations, graphs, left and right boundaries, everything straight up. Second problem, equation, graph, determining left and right boundaries, and then going forward. Problem 3, I'm going to go to the fuzzy screen, sorry, and I'm going to sneeze. Sorry. Oh, I have to find my hand sanitizer, but we'll do that in a little bit. Nope, that's not it. Sorry, distracted. Problem 3, nothing given. Equations given, got to give that, but no graph, no boundaries, which means I should be looking for intersections. So part of my job on this is going to be creating these graphs. Now, you've got calculators that will do that for you. So we don't have to go through all the algebra 2-ness of sketching the graph of a parabola or graphing this line. I'm going to do it pretty quick here. The line has a y-intercept of 5, up 2 over 1, up 2 over 1, down 2 over 1, down 2 over 1. All right. So there's the line. For x squared plus 2x plus 1, 0, 1 is definitely a point. So 0, 1. I also happen to know that -1, 0 happens to be a point. Okay. I've graphed, and if I graph this on my calculator, I can look at it and I see pretty quickly there's one of the intersection points. And so here comes the parabola once I get sort of an idea of where the vertex is. I can use that. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. That one? Okay. So there we go. That and that. Okay. I've done this the third time I've done this problem, so I kind of already knew some of this stuff in previous classes. I don't think I have it up anymore. Nope. I pulled the calculator out and graphed these. Okay. Looking at the graphs, I can see I've got a nice intersection point at x equals -2. I've got another intersection point at x equals 2. The area that I'm calculating is that thing. And so this is kind of where if we were sitting in class, I would work on getting an answer from you. Looking at this, my top function is the line. Right? Top minus bottom. When I say top, sort of like you're standing on, if you're standing on the x-axis, which one would be up higher? So if you're standing right here, there's you know, the line is higher than the parabola. So this will be 2x plus 5 minus x squared plus 2x plus 1 dx from -2 to 2. Okay. No, that looks incredibly intimidating. You're like 1, 2, 3, 4, 5 terms to work with. That's where you definitely make your life easier if you look at combining some like terms. You know, the fact that the 2x here with the minus helps you. The fact that we've got the 5 minus the 1 helps you. We've got some simplification that we can do. So we're going to end up integrating from -2 to 2, essentially what is 4 minus x squared. If you simplify, combining the like terms, you often can get a much easier function to work with. I'm not trying, if you're thinking like, well, what if they don't cross at nice places? Well, that would definitely be a challenge. We would have to use our calculator or something else to determine the crossing places, the intersections, the left and the right boundaries. I'm not putting that in front of you this time. If there's another option where these are not actually functions and we have, instead of top and bottom, we have left and right, there's actually problems where we're looking for an area, we're looking for like 2 areas and the top and the bottom switch, and so we have to do 2 different integrals. There's all kinds of variations for these. We're sticking to just kind of the most basic, like I said, we're sort of sticking bare bones. What are the basic things that you would see? All right, so 4x minus x cubed over 3 integrated from -2 to 2. You can see that there's an area here. So as much as you might start thinking, oh, this is going to come out to be 0, or you're going to get a lot of numbers that are similar, the answer is not 0. Okay? You can see an area, a shadable area between these two functions. So that means that this integral's value cannot possibly come out to be 0. So 8 minus 8/3 minus -8 minus -8/3. When you see things like that, you get really tempted and you want to be like 0, everything cancels, but it doesn't. Okay, so 8 minus 8/3 minus the quantity -8. And so this ends up being 10 and 2/3, or, yeah, 32/3. All right, so like I said, sort of building up our scale of difficulty. Everything spelled out. Graph given, left and right endpoints given. Oops, undo. Everything given. Write it up and go. Some stuff given, other stuff having to be read from the graph, so having to interpret left and right and get those in the right place. But once we do that, make a derivative and go. Making our own graph and determining the intersection points What I didn't do on this problem, but I could have if we wanted to try to kind of ahead of time figure out the intersection points. You know, if I did x squared plus 2x plus 1 equals 2x plus 5, okay. So that would mean that x squared, and then these would subtract away, and then minus 5 minus 5, x squared minus 4 equals 0. I can calculate those intersection points, okay, that these two functions cross at -2 and 2. And you know the negative one, whichever one is lower would be the left. So -2 to 2, it's just a matter of then you have to figure out, okay, if it's going to be for -2 to 2, which function, but in this case, graphing the line, I think, and then we know what's the parabola, that this is a regular right side up parabola, so we should be able to get there. Okay, so we're going to do one more, even though we have two more. We're only going to do one more. This is the one I'm going to skip. I'll let you pull this one out and practice it. You'll have the key to look at your answer. It's two parabolas. Definitely graph this on our calculator and see that we've got a regular parabola and an upside down parabola, and kind of helps you figure out that this guy is the one that's on the top because he's upside down, and this guy's, wait, yeah, I think it's like that. So, but that's kind of more, that's pretty similar to problem number 3. I want to go ahead and do problem number 5 to wrap things up. Now, on problem number 5, you're like, what the heck does that say? This is the function 1 over x squared. Okay. And then this is the function, so this is y equals 1 over x squared, and this is the function y equals 0. Okay. And you can see you have the left and the right points given to us. So that's going to be clear that our left boundary is 1, our right boundary is 5. Okay. Graphically, y equals 0, well, that's just the x-axis. So there's the y equals 0 graph. A function like 1 over x squared, it's not necessarily one we know off the top of our head, and we could absolutely put it in the calculator and look at it, but I like to talk about it because it's actually one we can figure out pretty easily. 1 over x squared is equal to the quantity 1 over x squared. Now, 1 over x function is that guy. We should know him from pre-calc. He's one of our parent functions. He's kind of the parent function of our rational function group. Piece here, piece here. When I square him, basically that just makes this guy, the bottom little piece, flip up here. It makes all the y's come out to be positive. And so I'm going to take that away, and I'm going to finish I'm going to redo 1 over x squared function. Looks like that. It's 2 of these curvy branches, one in quadrant 1 and one in quadrant 2. There's a vertical asymptote and a horizontal asymptote. So the piece that we're interested in is this guy, because we're interested from 1 to 5. One of the points on 1 over x squared is 1, 1. So we'll have this curvy piece. Technically, we have this curvy piece too, but we're not super interested in him because we are calculating the area between this curvy guy and the x-axis from 1, 2, 3, 4, 5. So it's a teeny tiny little area. Okay. So I like this problem because I like graphing 1 over x squared. I like talking about that. I also like this problem as a math teacher, as a calculus teacher, because in this problem we need to integrate 1 over x squared. We're going to integrate from 1 to 5, 1 over x squared minus 0. Because this is our top function, y equals 1 over x squared, and our bottom function is y equals 0. Now, integrating that, 1 over x squared, always fun. Not a natural log. I know if you watched and did last week's lesson, you might be like, ooh, if that's a natural log. If it was 1 over x, it would be natural log. But 1 over x squared, that's just, oops, let me go over here. I'll go over here and do this. So this is from 1 to 5, x to the negative 2 dx, because 1 over x squared is equal to x to the negative 2. So that's x to the negative 1 over negative 1 from 1 to 5. Not going to be a negative answer. You definitely see a positive area there. So this is going to be 5 to the negative 1 over negative 1 minus 1 to the negative 1 over negative 1. And if you get through that, that's going to be negative 1/5. Oops, negative 1/5 plus 1. Final answer, 4/5. So that's just a little bit more fun in terms of if you're a geeky calculus teacher like me and you're like, ooh, it's a more interesting function to graph, 1 over x squared. It's a more interesting function to integrate, integrating 1 over x squared or x to the negative 2. You know, numerically, you may have felt like this was going to come out to be negative, but because a 5 plugged in compared to a 1 plugged in ended up with this, we are still getting a positive answer. Oh. And we'll put that answer right back there where it belongs. Okay, so for this week's work, okay, and so just a reminder, last week's work was some practice antiderivatives and practice fundamental theorem, and it included antiderivatives for x to the negative 1 and for e to the function of x. The video for that's posted, the notes are posted, the assignment is posted. That's still out there for you to do. What I'm going to ask you to do for this week's work is kind of similar to what we would have done in class. I have a textbook page already scanned for you. Okay. And so the problems that you're going to do come from page 357 in the textbook. You're going to do problems 1 through 4. And 1 through 4, the graphs are there. And the region is shaded. And you just have to put the integral together and solve it. And then 9 and 10, make sure when you do 9 and 10, you make and show the graphs that the graph and the area and then your calculation. Okay. Questions about that or about anything else, calculus or non-calculus related? Anything else I can bring to the table? See who's all here. Look at all you fun people that are here. Hi, everybody. Okay, guys. Well, that's all I've got for today. Like I said, I will, as always, upload the video, upload the notes. Why don't you hang on for a minute, Afrin, and we'll talk kind of once everybody logs off. You and I can talk individually. If nothing else, kind of generic, then that's it. That's all I got for today. You're welcome to log off. Have a good morning. Good luck on any AP exams that you have for the rest of this week or next week. You are welcome. Have a happy Thursday. Have a happy weekend. See you next week. Remember, you can come see me in office hours. Ring the bell. You're welcome, everybody. Have a good day. Okay, so question about your grade. Here, if you want to, I can put you, let me give you a mic if you want to ask it, or you can type it. Either way. Hang on a second. Okay, go ahead. You can unmute your mic if you want to ask, or you can type it.
Hello, Ms. Willenbrock.
Hello.
I was wondering about like the fourth quarter grades. Like I have an F right now.
Well, the fourth quarter grade isn't really going to be a grade. What we're submitting or what we're putting in SIS is just whether or not you've completed the assignments that we've given. And so since you haven't completed any of the assignments, that's probably why it's showing as an F right now. That is not going to get averaged as an F. Just whether or not you complete the assignments and how you complete them is how I end up deciding either your course grade is the average of quarters 1, 2, 3, or I can take that and bump it up one grade level based on the work you've done. So that's why it's saying an F right now. It's because you have not. I have to document who's turning in their work for the quarter.
So,
Okay?
so I've been like getting C's a majority of the year. So if I do all the little work that we're doing right now, what grade would it bump it up to?
Okay, let me grab my thing here. I think I have everything. I was trying to make a note for everybody, so if they asked. Okay, so what I have right now, I believe, yes, is you have a C average for the year. You have, through your doing the online assignments, that would give you the possibility of having your grade increase to a C plus. So that's what one grade level is. So that's up to you. If you want to do the work and turn it in and potentially earn a C plus for the course, you can. Or if you don't do anything from this point on, you're going to get a C for the year. Okay?
Okay. Thank
Okay.
you.
You're welcome, sweetie. Have a good day.
You too. Thank you.